I'm Jeremy Tucker. I'm the business program owner for AUD for Edison. I've been with the company for 15 years. I was 5 years in planning and design, and then 10 years in supporting and managing AUD.
Hi, I'm Ernesto Regoza, or I go by Ernie. I'm the senior specialist. Been with the company 19 years, 17 years mapping, planning, and design, and 2 years in supporting AUD.
Just a quick look at our current system. We're on Autodesk Map 3D 2019, Autodesk Vault Professional 2019. We're on Automated Utility Design 846. We'll be going to 848 in October. UDH EAM implementation and UDH GIS. The things we're going to cover today, this isn't exhaustive, but just kind of a peek at some of the things that we touch and are doing with our standards inside of the tool. We're going to look at underground conduit design standards, cable pulling limits and validations, transformer loading and max cable amps, and pull heads. We'll start out with the underground conduit design standards. Some of the things that we'll cover is radius definitions, when to use bends versus sweeps, horizontal turns versus vertical turns, how we handle primary, secondary service and mainline trench. We'll look at the automatic generation of bends and sweeps, and then also overriding the standards rules for bends and sweeps. So this is straight out of our standards book. This is how we apply our standards to conduit design. The first thing is all of our bends. This is the definitions for the standard bends that we use. 36 inches bends for 3-inch conduit, 48-inch bends for 4-inch and 5-inch conduit, and 60-inch bends for 6-inch conduits. The minimum radius for all of our sweeps is 12.5 feet. Sweeps shall be used for all three-phase primary horizontal turns. Bends are used at the bases of primary risers and for secondary or service horizontal and vertical turns other than mainline trench. For single-phase residential cable runs, bends may be used for primary horizontal turns. And use sweeps when installing 600 volt 700 CLP. Now try and remember that every time you go to draw something. So essentially what this turns into is I made a table here that kind of defines primary, secondary, and service. This is the table for single phase. So you'll see that we have the 36-inch going all the way across for the 3-inch, the 48-inch going all the way across for the 4, and the 48-inch going across for the 5, and the 60 for the 6-inch. And then when we install 700 cable, it automatically goes to a sweep. Ernie's going to come up and show you a demo of how this runs.
Okay, so what we have to do first is we have to go set up our models. So first thing that we're going to do is set up the 6-inch. So you're going to see the first one here on the left. Here, you're going to see that it's a 6-inch. So 6-inch, you're going to see once we hit the enter button, you could see that it's now a 5-inch bend. And then we go to the secondary. It's a 3-inch conduit with single phase secondary wire. And then the next one will be a 4-inch conduit going into service, so service cable. And then next you're going to see that we're going to go ahead and show the radiuses. So for the 6-inch bend, you'll see the 5-foot radius. For the 3-inch bend, you'll see the 3-foot radius, and the 4-inch bend, you'll see the 4-foot radius.
This is the table Basically extended out for our three-phase. Just similar, you'll see that all of the primary is 12.5-foot sweeps, and then the bends continue on down the line with the same sizes as we had before. And then you'll notice that the 700 cable also has the 12.5-foot sweep.
And here, basically what we're going to use is the same drawing that we had before. The only thing is now we're actually going to change the model. Instead of the 1/0, we're going to do 1500 cable, which is three-phase. You're going to see once we do it, it does the 12.5 sweep. And then on the next scenario here, we're going to add primary line with duct. Since we set it up to 1500 cable, once we put it into that segment, you're going to see that it changes to that 12.5 sweep. So here, what we're going to show is that we could actually manipulate the bends by going to the feature asset, and where is it at? Right here, lock and bends. It's right set to true. We're going to set it to false. Once we do that, then we could go ahead and change the bend and sweep. So here you see the 90-degree bend 3-inch. We're going to go down to a 90-degree sweep 3-inch. And now you're going to see that it changes to the 12.5-foot radius. And then for this last one, we're just going to add a duct. So when we add a duct, the way it's set up in our system is that it sets it to primary. So it knows that the primary was at 1500 cable, so it knows that it's a 12.5 sweep. So what we want to do is change it to a service. So what we do is we go into the feature attribute, we change it to service. Once we change it to service, we're going to go to a 4-inch. And then we're going to go ahead and change the cable size to 700 CLP. And once we do that, you'll see that it updates to the 12.5-foot sweep. And here we're just going to show the radiuses, but they're all 12.5 foot.
So the nice thing about this is you don't really have to think about what you're doing when you're drawing. So it's looking at if it's primary, secondary, or service, and then it looks at if it's single phase or if it's three-phase. One of the drawbacks to programming it that way was that if you need to change it from a bend to a sweep and it doesn't match the rules, it always would force it back. So that's why we added in the unlock bends and sweeps, because there are those cases where you need to change it. And then also, like Ernie was explaining, we have independent control over the sweeps, but we also have control over the ducts themselves too. We can change them from primary, secondary, or service as well, even if they're empty. So. All right. One thing I was going to say was when we were putting this together, I was like, well, why does anybody want to see us draw this? It's just drawing. It does something. It's not until like you actually think about what it's doing and look at taking your standard and converting that from words into actions that it's actually doing a lot behind the scenes, and you don't necessarily realize it. Cable pulling limits and validations. So for cable pulling, we basically validate on 5 things. We check the duct size by voltage and cable size. We check the max cable length. We check the max cable tension by the structure lift plate rating. We check the max tension through a sweep and the max tension through a riser bend. So this is straight out of our standard. This is what a planner would go and look at. Before, we used to do this by hand. And we still have like even an Excel sheet that kind of does well, it does equivalent pole length. It puts everything in feet, but it's not in tension. So we moved to tension in the old AED before we moved to the new one. And then now we've kind of even extended what we were validating from the old one moving to the new one. So if we come to this table, the first thing we're going to do is we're going to find what voltage that we're working in, and then we're going to go find the cable size that we're looking for. And then that'll tell us what is the appropriate conduit size per our standard. Go ahead, Aaron.
Okay, so for this example, we're basically going from a vault to vault, and we're going to go, it's about 500 feet, but we're going to use a 4-inch duct with million cable. We know per our standards, you cannot do it, but we just want to show you that there's validation alerts that will alert the user that they cannot use that type of conduit. So as you can see, we're going to go from vault to vault. Once we go ahead and hit enter, you're going to see the primary comes in. We'll insert a call out. And what this call out is going to verify is that it's going to say over max. Over max meaning that the crews cannot pull the cable. So in this case, it's failing both directions, but it's failing both directions because of the validation. It's basically saying 4-inch duct and 3 million cable is currently not defined in our standards. So what we're going to do is just go ahead and update the conduit to 5-inch, which it is in our standards. You can see now we don't have the over max result. We actually have pulling both directions, and it's passing. You'll see the green check marks, and it's passing both directions.
This is just a closer look at the note that the designer gets when they open up and look at it. So in this case, it doesn't actually give a standards reference. It says it's not in the standards. So it's an automatic fail. You know, this is something that we put in more recently because there were some sizes that people were using that weren't per the standard, and it was just running and giving a result when really, it's not according to our standard. They shouldn't be designing that way. So we added this in. The next one is the max cable length. So we're still working from that same table. So we're going to go to the voltage again. We're going to go to the cable size, and then we're going to hit the column on the end, the max available cable length. So that's how much cable is available on the reel. So we don't want to pull, design something that we don't have enough continuous cable for.
Okay, so in this example, we're going to do the same thing, go vault to vault. But in this case, we know that the standard says we can go over 20,000 feet, or 2,000 feet, I'm sorry. So in this case, you're going to see that we're at 2,050 feet. We're going to go ahead and add the 5-inch duct with 3 million cable. Again, we're setting up the model, 5-inch, 3 million, and as you can see on the profile, it says 3-phase. So once we add it, and we'll go ahead and insert the call out again, and you'll see that it's overmaxed on both directions. So we know it's failing on both directions because it's over exceeding the 2,000 feet. And we go to the analysis, we go to pulling tension, and once we go to the error, you could see that it exceeds the max length of 2,000 feet per the tables.
Just another quick look at the note, and you'll see that this one actually does refer to the standards table because we did have a defined standard for it. So it's saying DDS table 918. So That's helpful to the designer to know where all this stuff is coming from. The next one is the max cable tension by structure lift plate rating. Down here in the bottom notes, it says that the structure lift plate rating is determined by the structure size and the type in general. 10,000 pound swivel is applicable to pull boxes, manholes smaller than 6x8. In general, the 20,000 pound swivel is applicable for vaults and manholes of 6x8 and larger. Then we have another standards book that has all our structures in it, and this information is available in the standards book. But basically what that's going to do is it's going to tell us which column. If you look, we have the 10,000 pound swivel and the 20,000 pound swivel column. That's where we're going to actually go pull our numbers from. In this case, our example that we've been using is vault to vault. So we're going to use the 20,000 pound swivel, go by the voltage, go by the cable size, and then you'll see in the parentheses the 9600, that's our limit in pulling tension pounds value. And then we'll jump to the example. Oh, sorry. This is just because I didn't want to go through and find all of the structure references. The lift plate rating is actually put on the feature in the configuration for all the structures. So you'll see in the column, some of them are 10,000, some of them are 20,000. So it actually does a lookup, what it's connected to, so it knows which value to pull from the table.
So again, we're doing an example of vault to vault. Example is going to be 1,000 feet to the east, and then we're going to do about a 22-degree angle going south, about 900 feet. So again, we're going to set up the model to 5-inch duct with 3 million cable. And it's 3-phase. And then now we're going to go ahead and insert the call out. And as you can see, it's overmaxed in one direction, but it's actually passing in the other direction. When we go to the pulling tension calcs, once we go here and select the validation error, you can see that it's saying that section 4 exceeds the max cable tension of 9,600 pounds per the DDS tables.
And there's just a quick look at it again. Next one is max tension through the sweep. Again, we're going to go by the voltage, and then we're going to go by the size of the sweep. Or sorry, go to the cable size, and then the conduit size. And so in this case, the max tension would be 6380 going through the sweep.
Okay, this example, we're going from vault to vault, but sometimes, obstacles out in the field, there is typical cases we do have to do this because of existing structures or, for instance, rocks or whatever it may be. We just wanted to show that that it does fail. So we're using a 45-degree angle, which we typically don't like to use. But again, we're setting up the model. We're doing 5-inch, milling cable, 3-phase, and we're going to go ahead and add the primary line. And again, we're going to go ahead and add the call out. That way you could see that we get the overmax for both directions. We know it's failing. We go to the analysis tab, go to the pulling tension, and once we see the results, you could see that it says three-phase conductor tension at section 9 through this bend/sweep or Y fitting exceeds the threshold of 6380 pounds per the DDS tables.
And there's a quick look at it up close. All right. Next one is the max tension going through a riser bend. Again, go by voltage, your cable size, and then whatever size that your riser bend is. So this is like your riser bend at a pole, at the base of a pole, or like going up into a surface mount structure. In this case, the limit on this one, the example we're going to do, would be 2741.
Okay, in this example, we're going from a pole riser to a vault. We're going 100 feet to the east and 75 feet to the south. Again, we're going to use 5-inch duct with 3 million cable, three-phase as well. And once we hit enter, it does all the validation for us, and we go ahead and insert the callout. And then from here, we're going to go to the analysis tab. We're going to go to the pulling tension calcs, and we're going to go to the one that fails. And here, it's basically telling us that it's failing in the bend, going up to the riser. So what we can do here is we can go with a 6-inch fiberglass bend. So again, we're going to go and unlock the bends and sweeps right here. And once we do that, we could go ahead and go to the sweep. We could change the bend to a 90-degree 6-inch fiberglass. Once we update it, automatically it updates the pull tension, and you can see now that it's passing.
That's actually kind of a weird scenario, but we do that all the time just to get a little bit extra, without having to up the duct size. If you might have noticed that our call out didn't say overmax, we found a scenario when we were doing this where we missed the rule for that one. So we do need to add that in. One thing that I would say too, though, the call out's nice, but one of the things that we have found is that people don't actually go back to look at the analysis and they rely on that call out all the time. So we might revisit how we do that just because we want people's eyes to actually look at what happened, in that analysis more and not just be like, oh, it says it passes and we're good to go. So just a side note. The next topic we're going to cover is transformer loading. This one was actually kind of hard to narrow down because this actually gets done as part of our voltage drop and flicker trace, and we're doing all kinds of stuff with that, and so trying to figure out exactly what to share with you guys, narrow it down. So this is a little bit, but I think we got it. So some of the key components that go into transformer loading for us, information that we're actually looking at from our design is climate zone, the customer type, our coincidence factors, or I know other utilities call it diversity factor, install range, and the removal point is what we're going to be using. All of our service territory is divided up into climate zones. So we have actual tables. I'll show you one in a couple slides here that have all the different information. So We have different loading requirements by the climate zone, so the install and removal range might be different by climate zone. I think we actually have an example of that. But this is the first thing that we look at. This is actually stored on the transformer, so this gets set on the transformer itself. The next thing we look at is the customer type. This is really more of like residential type example that we're going to be showing. The thing we'll be looking at is we have single family developments, multifamily developments, and then now we have electric vehicle added into that as well. We don't have, the standards aren't as clear as that. It's mostly examples right now, so that's why I don't have it like written out as concise as the other ones are. This is our table for coincidence factor. You'll see on here that we have those different customer types, right? We have the single family, which is in the tool, we call it residential, multifamily, and electric vehicle. The way that we're actually using this is what we do is we find the number of existing customers and the number of new customers by customer type. So it would it's going to do a trace, and it's going to say how many single family customers are on here, how many are existing, how many are new, and then basically you go to this next section up here and you find the number, and then you'll find your value for the coincidence factor. Once you have found the coincidence factor from the table by the total number of customers, then you're going to multiply the new customer load by the coincidence factor. And then you go back and add the existing customer load plus the new customer load. And then you total all of the load from all the customer types. So a lot of stuff happens in that, in that trace when it's doing this. And then you have the install range and the removal point. So this is just a picture of like those tables that I referenced in that first slide with the climate zone. So each one has this. At the bottom, you've got your install range and your removal point by transformer size. So in this case, this was climate zone 1, so 25 kVA transformer. Our install range is from 0 to 38 kVA. And then the removal point would be once it hits 60. I didn't actually include an example for removal point, but we're going to look at the install range. So this is kind of like before we do the actual demo, because the demo, it just happens and you don't know what happened. Because that's what I meant earlier when I said the nice thing about AED is it does all this stuff for you, but if you don't know what it did, it's kind of, so this is our scenario that we set up. If you look, coming off the transformer on the left, going to the south, we have a new non-dwelling EV. So that's an actual customer type inside of the tool, the non-dwelling EV. So we're going to add 6 kW there. In that middle section, we have 2 existing residential customers, and those will be 6 kW each. And then on the next set, we have a combination, a new residential with 6 kW of regular load and 6 kW of EV load. And so actually all 3 services, I set them up the same like that. So really what this is doing, if you look at the bottom, we have existing residential. We have 2 customers, which account for 12 kW. We have a new residential customers. We have 3, which account for 18 kW. And then new EV customers, we have 4, which account for 64 or 24 kW. So this is kind of like a spreadsheet I made for myself when we were implementing this to be able to double check what we did. But it kind of helps, narrow it out. So the first section up here, single family, I had 5 customers total, right? So that was new plus existing for the regular load. And then the load gets split into existing load and new load. So I have 12 and 18. And then what happens is, since I have 5, I go to the column for 5 for single family, and I'm going to multiply the new load by 0.72. And then I'm going to add the existing and the new together. Then I take all that EV load, and I have 4 customers, and it was all new, so it's going to be 24. And then I'll go down and I'll find the EV in the coincidence and go to the column for 4. So I'm going to multiply all that load by the 0.79. And then at the end, I should have 43.92 kW and 48.8 kVA on that transformer. So now we'll actually go show you what it does. Oh, I guess I'm gonna do this one. Right? So we kind of pre-drew the secondaries here. We're just gonna add the services and show you setting the customer types and the load on it. We already had set the transformer, and on the transformer, we already set the climate zone. So we're working in climate zone 1 on this one. So now he's going to go to the meter. So we have a service point, and then we have the panel, and then we have the meter. And so we've extended our trace to go all the way down to the individual meter. So I could have, like in a multifamily situation, I could have 20 meters, and I'm going to go be able to pull each load and each customer type from each meter going back and do this same thing. So right now he's updating the load. So we split it into 2 fields. We have load for regular load, and we have EV load. So he went and added the EV load. Now these 2 middle ones, these were the existing customers. So we're gonna draw them out. They'll have the load by default because we default to 6. That's why I used it in the example. And then we're gonna set the status on them to existing. Now the last 3 that he's gonna draw, these are all new, and these will all get the regular load plus the EV load on all 3. Sorry, we don't draw very fast, so the examples go kind of slow, but hopefully it makes sense. Now he's going to select all the meters and update the load. So we're just going to look at the transformer here. And I think I have a screenshot of it so we can look at it a little bit closer. But there we go. So we're sending a message out right now. It tells you what the diversified load was. So all those calculations, things that I did before, basically says that we had 43.92, which is what I had when I hand calculated it, and the 48.8 kVA. And then at the bottom, you see it validated against our install range table. And since we had 48.8 and the install range only went up to 38, it failed it. So that's how we do loading. The actual KW on the transformer itself, it stays as the absolute value. So this is just for sizing purposes only that we're doing this. Yeah, I think that was it on that one. Yes. So he asked if we factor in like voltage differences for solar and that stuff. So right now, I think most of that stuff is being handled like on the primary side in the calculation on how they're handling that. But you know, this was kind of like phase 1 of our implementation of some of the new EV standards that are coming out for us. So um, I don't have like a solid answer for how they're handling that. I'm not an engineer, so this just gets handed back to me. So yeah. All right, next one will be max cable amps. I mean, this is going to be similar to like how you saw our cable pulling stuff, but this also happens in our voltage drop trace. We have a table. We actually have several tables, which is kind of, I guess, what I don't know if that makes us unique, but I just remember when we were doing our configuration, that we had to do some extra work to be able to put all these in and validate all this stuff. So we're just going to look at a single phase, but we have multiple different ones for three phase, like for three phase and cable trench, three phase and duct banks, and all kinds of stuff. But in this case, we're just going to look at a simple single phase example. The cable size is 1/0 for our, this could be secondary or service. Number of runs in a duct bank. So we have the max amps by the number of runs in the duct bank. In the first example, you'll see as you go down the list, it derates, the cable amps, the more ducts and ducts and cables that you have in the trench. The first example that we'll look at will be just a normal run. It's going to validate against just one run in the trench. The second example that we'll look at is we actually have an amp rating for if it's in a riser. So the tool recognizes that it's in a riser, and will use this validation. And then last one, climate zone comes into play. So climate zone 9 for us is desert area, so it's like super hot there all the time. So we derate that also. In the note says take all these ampacities and multiply them by 0.96. So the tool's handling that as well.
So this first example we're going to do, it's a 25 kV transformer. Climate zone is 1. We're going to go ahead and add a service. Once we add the service, we're going to go ahead and update KW demand. So we'll go ahead and select the meter. We go to the actual meter. When we go into the load, we're going to select 50. Once we hit enter, it runs the analysis. And we could go ahead and check the voltage drop for the conductor. And you can see that it gives us a validation message saying that the amps exceeds 172. As you can see, it's 231. What we're also going to show is that we could change the climate zone. So in this case, we're going to change it from the 1 to 9. And we're going to rerun AUD voltage drop. That way it runs the voltage drop again. We'll select the transformer. Runs the voltage drop, and then we could go back and check our results. And you can see we get another validation saying that the amps is exceeding the 165.2 per our standards. And then again, this is just showing some screenshots of the validation alerts. And now what we're going to do is we're going to go ahead and show you guys an overhead. Actually, we're going from a riser, so overhead pole, down to a underground service. Again, we're going to select 25 kV transformer, climate zone 1, and we're going to go ahead and add the service. And once we add the service, again, we're going to change the KW load or demand. So we'll select the meter. Go ahead and select the meter here. And the load, we're going to change it to 50. And then we're going to go ahead and go to the analysis, check our voltage drop, check the conductor results, and you can see that we get the result there.
So you see, it kind of just follows along with that table. You know, it recognizes how you designed it, what it is, and knows what to look for, and then it validates accordingly. Last thing we're going to talk about is pull heads. I don't know if you guys have had to work with pull heads, but that's always a fun thing to do, setting those up. Some of the things we'll talk about is the construction type, or deviation angles, dead ending cross arms, wildlife protection, and covered conductors. So these are things that we have kind of implemented as standards into the tool so you don't have to think about it. Our construction type, so our standards, we don't actually have like standardized pole heads. So you'll see tomorrow our counterpart from transmission, our transmission group has standardized pole heads. So you can actually go into their standards manual and find, it's like TOH 301 and it's like a complete kit. It builds this pole head. We just have general rules like this is standard straight line construction. This is how you do turns. This is how you dead end. And then it goes across and adds all other kinds of things to it. Like we talked about wildlife protection and all these different things. And there's all different kinds of construction types. So all that to say is it's not like super cut and dry, like just saying, oh, just use this kit every time you use this model. We're actually building these on the fly. So with the standards rules that we did. One of the things that we put in here was deviation angles. So how does it know when you're doing turns? Should I use a single arm or a double arm, or should I double dead end, or should I use a buck arm? So this is what our standards the planner would go look at. For the example that we're going to show in a minute, we'll use 1/0, and you'll see that the limiting deviation angle for a single arm is 20, and then for a double arm, it's 40. And then this is the double dead end, and the max angle for a double dead end is 60. This is a look, this was the easiest way to show it. This is actually from our spreadsheets, from our configuration. We're actually using we're using the model sheets, and we have a custom table that has other information on it as well. But the main thing I want you to look at here is this is all the parts of how we would do a standard straight line. So we have the top line is just a straight line pole. So if it was a through pole, that angle, if you look to the far right, is 0 to 1. So if you're within that range, it's going to always place it as a straight. The next one is a single arm. So if that angle is between 2 and 20, it's going to place a single arm. If it's between 21 and 40, it'll be a double arm. And then 0, 0 is dead end. Double dead end is between 41 and 60. And then the dead end with the buck arm is 61 to 180.
Okay, so first example that we're going to show, or first we're going to set up our model. We're going to use three-phase standard horizontal construction. And again, like Jeremy said, we're going to use 1/0, so it'd be ACSR, 1/0, 3-conductor. So once we set up our model, we're going to go ahead and do a straight line construction. So we're just going to go pole to pole, and this will be at 0 degrees. And one thing Jeremy didn't mention, we decided to do these videos, these demos, that way we don't fumble during our presentation. So that's why it's taking a little bit. But when we select the pole head here, if you go to the pole head, which is our cross arm, you can see that it's standard straight line construction. And then next example, we're going to do a deviation angle of 15 degrees. So we'll go ahead and do our first pole. And then here we're going to select 15 degrees. We're going to select 200 feet. Once it does the validation, we'll check the pole head. And since it's under 20 degrees, it's going to, when we select the cross arm, it's going to select the 12 kV angle single arm because it's still under the 20 degrees. And now we're going to go to next example, deviation angle of 30 degrees. And here we're going to select 30 degrees. And since this is over the 20 degree, we're going to, once it does the validation, we select the cross arm, it's going to do the angle double arm. So it knows that it's past the 20 degrees. And then next example, we're going to do a deviation angle of 50. Again, still using the same 1/0 cable or conductor. And an angle of 50 degrees. And since this is over the 40 degrees, construction says we should do a double arm. So once we select the pole head, you could see that it's ordering the double dead end construction. And then the last example, we're going to go past the 60 degrees of a deviation angle of 62. And in this case, we know that it's past the 60 degrees, so it's a buck arm construction. So once we go ahead and set the angle to 62, hit enter, does the validation for us. And we select the pole head. And you can see there, it does the dead end with buck arm construction.
Just one note too on the angle arms and the other stuff, it also picks the correct insulators that go with that because we have different kits for angles and that type of stuff. So we have that, where we have the kit that it picks and all that. So, but probably the most understandable critical part was the cross arm going right there. In dead ending, by conductor size, full tension is what we normally do. We haven't set up reduced or untensioned guying in the tool yet. But for the same example, a dead end, if we are doing 1/0, should have a double arm. Wildlife protection. So we have, rural areas. California, we have a lot of protected wildlife, eagles mostly, different hawks and stuff. So very critical that we construct this right. Otherwise, we can get sued. So our standard says in an eagle zone, the main thing to take away from here says the last sentence, spacing and covers shall be constructed per, our other standard number. Basically, we put covers if you have, 3-wire or 4-wire. 3-wire gets 1 cover, 4-wire gets 2. The other thing to notice, if you're using cover conductor, which we are doing a lot now because of high fire, so we have gone and replaced miles and miles and miles and miles of conductor with covered conductor. And in those cases, we don't have to use the hoods because it's covered. And I'll actually show that on the next slide here. So as you can see in our standard for cover conductor, we don't need to have the hoods, but on the dead ends, we do have to put covers on the dead ends. And so we want to make sure, that this is one thing because we were doing so many projects like this and a lot of designers were missing this. So we actually added these in so that they're more automated and they don't have to think about it as much. And we are going to go back and add some more things now based on the type of work we're doing as well. And then this demo will kind of show all 3 things that we just talked about.
Okay, so for this demo, again, we're going to set up our model. We're going to do 3-phase. We're going to do standard horizontal construction, and we're going to use 1/0 ACSR. Once we select our model, we're just going to do just a simple straight line construction. This time we're going to use 4-wire. And once it does the validation, we're going to go in and actually station the pole so once we select the pole, anything that we select, it's going to order that in our station callout. So here, what we want to show, it's full tension, and it's ordering the double dead end cross arm. And then we're going to go to this tangent pole here. What we're going to do is station just that pole. Once we station it, it's going to order what we selected. So it's going to order the pole and the pole head and the insulators. But what we wanted to show you here is that when we select the pole head, we get, if it does need the wildlife protection, all we need to set is the feature attribute to true. And once it does that, since it's four wire, it's going to order 2 of the avian hoods.
Does AUD know you're in avian zone based on where you're working, or is that just something the designer has to grab
That is
elsewhere
something
and know?
the planner would have to know. It's not in our standard.
But you can, if you do have it in a polygon in your GIS, it would know it's in that zone. Or you could set the whole work order to say, I'm in an aviation zone or fire zone, and those standards would apply. They just don't.
Yeah, that was, we haven't made it that far yet. So we do have like our service territories. We do have definitions of where those things need to go. And we are going to actually define some of that stuff. We're going to define climate zone and like contamination area and some of those other things through our GIS and bring that in and set stuff. That's like in the future. We haven't got that far yet. One of the things we are doing, like Pat just said, is we're just going to add it to the defaults for now so that they can set that attribute so they don't have to go on every, pole head and set it. They can just set it at the default so as they're drawing, it automatically do it. Just one other thing, it does know, like it looks at the number of wires because it does a count. So it knows the proper number to order based on what pole head that it places.